All right, this is like the last we talked about was like the n queens, right? And then we talked about how your choice of, like the moral of the story was your choice of representation can have a big impact, and it might not always be obvious, even with toy problems, let alone these complex problems that we're typically applying these algorithms to. And what else was I going to say about it? Whatever. We were playing around with different representations and how could it impact things and like the gap and all that stuff. So there are some common representations. There's nothing stopping you from having a different representation. You will notice in this list, I didn't talk about like a 2D chessboard representation, right? That we absolutely could have implemented for the n queens problem, but we talked about like why it wasn't great, but we could have implemented that. But that would be like a non-typical, non-standard, for lack of a better term, representation. Your common representations are going to be things like your binary representation. I kind of listed a couple of these common things at the top of the lecture, but something like a binary representation, like collections of zeros and ones, and you can use that to encode anything you want because it's zeros and ones. If you can encode it in a computer, you can encode it with zeros and ones. So, you know, you could encode anything that we would like to encode in the computer. But like this is like the classical encoding. This goes back like decades ago, what you would use. Then there were some like interesting properties about this encoding that are like interesting and valuable. But as time has gone on, like you're not jumping to use this encoding very often. It might be good for like if you had like a sequence of like Boolean questions. Sure, okay, something like that's great. But other than like having like binary decisions, it's not going to be overly helpful. That's not true. It's not going to be it's not going to be people's first choice. Okay? It could still work. And this particular representation it's like necessarily a very indirect representation, I suppose, unless you were doing like a binary encoding for a binary problem where there isn't really a translation process. But like, let's say you've got like literally maybe it's in blocks of 8 bits to encode some value or something, right? There would need to be some translation function to get from the encoding, from the genotype to the phenotype and vice versa. And by the way, with any of these representations, typically there will be like genetic operators, your variation operators, that are better suited for some representations than others. So with binary representation, maybe there's some neat genetic operators, like bit flip, for example, right? Bit flip's only really going to work for something like that. So in integer representation, this would be instead of a collection of binary values, you've got a collection of integers. This could be any integer or maybe an integer from some predefined set of integers. For example, allow all integers representable in Python, or maybe you want to have a list of the values 0, 1, 2, 3 from some predefined subset that might mean something like, well, that means like north, south, east, west or something, right? What's interesting here is the ordering of these integer values is not necessarily important. Basically, like maybe in this case, the fact that the number 7 comes before the number 8 is meaningful for your representation. But it's entirely possible that the orderedness is not meaningful in any way. Like, oh, 0 comes before 1. Does north come before south? I don't know. Maybe we can make some weird argument that it does, but at the end of the day, like you wouldn't do arithmetic on this to mean anything. Like you wouldn't say like, oh, west minus south equals east, right? Like that's useless, right? It's just like a stand-in label. You can make this argument almost with like TSP, right? Where, okay, I know we didn't use integers, we used permutations, but the same idea still stands where we are effectively using the numbers as a unique identifier for a city. The fact that it's city 0 and city 1 might not really be important for us. For some versions of the problem it might be, but in general it doesn't have to be. Yeah, okay, the order doesn't matter. Yeah, so like north is not less than south. I don't know. Maybe it does for your problem, but I don't know. The order of the elements in the collection may or may not also matter. This is interesting, right? So like the fact that the integer at index 7 comes before an integer at index 8, the order that they exist may or may not be important as well. It's all dependent on the problem. Like for TSP, it absolutely does matter, right? Because the order is the order in which you visit the things. So sometimes the ordering of the values, not like the orderings of the type, but the ordering of the values in your list could be important, but it doesn't have to be. This encoding really could be used to encode whatever you want as long as there is a sufficient encoding decoding method, your translation method. That's often called like a translation method when you're encoding, decoding. How do you get from the phenotype to the genotype and back? Encoding would be phenotype to genotype. Decoding would be genotype to phenotype, I guess. So yeah, consider the problem of programming a robot to traverse a maze. The set of possible integers could be 0, 1, 2, 3, meaning north, south, east, and west. The robot needs to take 10 steps, right? So a valid chromosome could be 0, 0, 0, 1, 0, 2, 3, 0, 2, 2, right? There. Yeah, cool. Yeah. Any questions about this idea? Awesome. So like in this particular case, something like a bit flip doesn't really work because it's not like, okay, turn it to the other value. Here, we might need to like pull from a set. Right? So it's not like, oh, turn a 0 to a 1, a 1 to a 0. You would have to say, okay, replace the 0 with one of these. Okay, probably randomly picked from a hat. Now we have a permutation representation. This is if you have an ordering of a set or a multi-set of values. When I say multi-set, I just mean like sometimes your sets might have like 2 instances of the same thing in it, and that's entirely fine. Just because set proper is defined as a set of unique values, right? But maybe you don't have unique values, but it's like a predefined set, right? So you can only have like all of these values in any ordering you want. The values don't even need to be integers. They could be whatever the hell you want. It's just like you have a collection of things and you want different permutations of those things. Is that clear? Cool. Like with TSP, we use the permutation representation. And how did we encode it? Well, we took each city and gave it a unique label, 0 through n-1. We could have taken each city by its real name as a string, like go from Antigonish to New Glasgow to Guysborough to whatever. Like we could have done that. That would be the set of things, and the permutation would be like the ordering of those things. Cool? Yeah? And maybe you have an instance of the problem where like you got to hit New Glasgow twice, once in the morning, once in the afternoon. So New Glasgow could be in there twice in the set, right? So it would be a multi-set, technically speaking. Yeah, so this is just an arrangement of some values in some sequence. Don't get overly focused on like integer value. It just values. These are useful for situations where each value in an encoding must be unique or have a fixed number of occurrences, right? For example, TSP. They do not need to be numerical. Order of elements in a chromosome matters. Consider the problem of finding English words with a given multi-set of letters, right? Below a list of possible chromosomes, right? Do you see what I mean, right? We've got this set of letters. Give me permutations that mean something. I don't know what, I'm guessing the first one doesn't actually mean anything. Right? But, you know, kind of, some of them are kind of cool, right? Look at that. Name tag, fun. Point is, unique value, well, a set of values. They're not unique, there's 2 A's. But you get the idea. Real value representations. This is like, okay, now you've got a collection of like real values. Now we're using computers. We can't truly encode real values, so we have floating point numbers, fine. But consider the problem of encoding weights for an artificial neural network, right? Evolutionary neural networks are a thing. The weights between the neurons, like attached to each edge, is some floating point number, right? So let's evolve them. Maybe you want to find the xy coordinates for some two-dimensional space to find the minimum value of some function. So imagine you've got some function, f of xy. What combination of xy gives you, like, here I'm looking for like the minimum. All right, so imagine this is the Ackley function. It's a well-defined function. It looks like this if you plot it. So the question is, what value for x and y gives you the smallest result for the function of x and y, or x1, x2, whatever, right? And for this particular function, it happens to be 0, 0, right? But the question is, like, can your search find it? You would need to use floating point numbers. Here, it's a continuous function. Sure, I know the best answer is 0, 0. But like you wouldn't want to use integers here because it's a continuous function where all the values in between each integer do exist within this function's like space. Questions about this one? Now something like a GA, your basic GA, can work with real values if you use like the right genetic operators. But typically, like one wouldn't go and do that. You could do it, there's nothing wrong with doing that. It's have fun, right? But there are other strategies, other algorithms like specializations of evolutionary computation that are particularly good with floating point values. And then like a tree representation, right? A tree representation is like the classic what one would use for genetic programming. Genetic programming is effectively using a GA to evolve programs or functions, right? These programs can be like something like a mathematical expression, and here's a tree. These are called like S expressions, symbolic expressions. I think I showed you an example of this on the board a little while ago. The idea is like you could encode this as a bunch of like, you've got like operators which might have some number of like inputs, and they return a value. And you could have like terminals. Some of them may be variable values, and some could be like some constant value. But this could be something like f of x and y equals 1.2 minus x times y. I guess it would be y times 1.2 times x, right? That would be like what that function encodes. You can mix, like what's interesting about this one is it's only, they would call this like untyped, even though that's kind of not true. It's like single typed. Right? There's numbers. These are numbers. What's interesting here is you're kind of like combining like different types here. Like this could be like a classification, right? Like, oh, if the length of the petal is less than 5.2 or it's not red, right? Like that's like what that is. It's still some expression, some function. Boolean operators, binary operator. Yeah, they take two inputs, produce like an output, but again, numbers, comparisons, returning Booleans, right? So now we're like mixing types. And then you could have like things as complex as like programming a robot, right? So like you've got like if then else, right? So you're mixing a whole bunch of different things where you've got like instructions and whatnot. You can use trees to encode things like functions. And the functions could be things like mathematical expressions or like actual program code. Cool. Yeah, and that's just showing you what they are, right? So if open and right close, then forward, else turn right, right? Like that's like what that is telling us. The trees are made up of operators and operands. Operands are the leaves of the trees, can be variables or some like constant value. And operators are like the interior nodes that act on the values of like their children and return whatever they do, right? Like less than will return a Boolean. Many of the common representations for evolutionary computation have a fixed size. However, trees so not. That should say do not. If anyone wants to make a pull request to fix this typo.
Oh, it's that. I haven't done it. Computer, man. I don't know if it's set up.
You could do it on the website. You can edit in the website. Okay, all right. I'm just saying. Then someone else can do it. Someone else can. Whenever you contribute to the GitHub page, you will be remembered from time immemorial that, oh, he's going to do it?
I can still use this.
Just don't let it go to sleep? Okay. Well, it's a race. Who's going to beat him? Who gets the credit for fixing that, you know? All right, anyways. However, tree, that really should be like trees do not. Yeah, I'm guessing, yeah, trees, and throw a D in there. And they can have odd shapes, right? Like there's some funny things with trees like we could just talk about here, right? Like you could have like the crazy trees that are like this, where you've got like, imagine you've got some like gigantic tree. There's like 15 layers. And it's going to do all these crazy calculations. Or true, right? Like, you know, it's kind of one of the funny things with genetic programming in the trees is you can get some weird stuff going on. You're not going to do it?
I also wiped my discs.
Okay. Someone else gets the privilege of contributing and getting full credit for all of that hard work of fixing this. Just think of the value you're adding for all future students, right? It's crazy. You get to say, when you get a job interview and they say, like, what projects have you contributed to? You can be like, well, let me tell you. I helped my professor make the course content, you know, blah, blah, blah. Right? And you can prove it by being like, here's my GitHub. You can see, it's right there. Just don't click it, because then they'll see what you did. And they'll be like, really? But, you know, you get to say you did it, right? Which is good. Anyways, that's the, oh, yeah, from the virtual, yeah. That's like the general high level, like your representations. This is not an exhaustive list. These are just like your common general representations that you're going to see. But there's nothing stopping you from having like a graph representation or having a 2D chessboard representation. You could do whatever you want, but your choice of representation will often come with choices for, like, will have like a necessary impact on your choice for genetic operators, your variation operators. It's going to matter. All right, N-queens, GA. So now here's what we're going to do. If you have a working computer, which, if not, just buddy up with somebody.
What are we doing?
We're gonna spend in-class time playing with the algorithm. Yeah, well, you've already cloned it.
Well, yeah,
It's wiped.
It's on SSD right now.
All right, so here's what I want to do. We're not going to, like, look, the last time, in fact, maybe we will spend more time, like today and maybe some of tomorrow or Friday's lecture, working through this one together. Wait, do I? Oh, wait, no. Right now I talk about it.
We're not doing anything yet?
And I think maybe the next topic is, okay, I jumped the gun. I'm sorry. I hate, okay, I'll just give you fair warning. This topic, I'm just going to describe an implementation of N-queens for the genetic algorithm, okay? Then the next topic is, okay, get it and play with it a little bit. The first time around, you might remember, we had that peculiar lecture where the class size tripled, and like literally tripled. And so we didn't get a chance to follow through on the lecture of playing around with the genetic algorithm. So because of that, like usually what I would do is this one, of experimenting, I'd give you a little bit of time, but we'd blitz through it. This time maybe I will give you a little bit more time to play with the experimenting with the GA, just so you know there's some, because that would be I don't know, we'll probably get to that Friday. So you'd get a chance to sink your teeth into it sometime on Friday, which is kind of nice just in case something funny came up before the assignment is due. By the way, what's nice about this implementation, if you haven't noticed, is look, ultimately we're going to use a permutation representation for this thing, right? And we're going to use genetic operators that are really good for permutation representations. Meaning, this will probably be exceptionally helpful for other problems you have to do that require a permutation representation. Something like TSP, for example. So this will probably help you quite a bit, especially if you're observing some peculiar behavior, right? The key difference, I suppose, is going to be things like your fitness evaluation. It's not going to be how you would do it for N-queens, but whatever. All right, so the purpose of this topic is to emphasize the differences and similarities, really the similarities between your typical GA implementations. We saw a silly example of that bit string maximization, right? Unsigned integer bit blah, blah, blah maximization, right? A couple weeks ago. Here's an N-queens one. And we're going to look at the implementation And you're going to be like, holy crap, it's basically the same as the other one. You just switched out the genetic operators and the representations, but it's the same. Okay? You're going to notice that. And that's the point of this lecture. We'll also just more exposure to an implementation of a GA. Okay? Yeah, so yeah, although it was a different problem, but it's kind of the same. So, problem. We're going to do the optimization version of n queens. Effectively, we're not looking for like the satisfaction, right, where it's like yes or no. We're looking for minimize the number of conflicting queens. It gives us that gradient, right? It says like if one has fewer conflicts than the other, we're going to prefer the fewer. Because otherwise, if it's yes, no, we really don't have much guiding force. That would be
until you get to a point.
Yeah, and then right, yeah. So what do? Given an n by n chessboard, place n queens on the chessboard while minimizing the number of conflicting attacking queens. In other words, minimize the number of queens in the same row, column, or diagonal. So the reason the optimization version of the problem, we already talked about it, right? So like we previously talked, we're going to use the permutation encoding because it's way better than it's going to be n factorial, which is way better than n times n choose, right? However, the previous is using is only n factorial, which is still not bad for small enough n's, right? So, okay, initialization. Before evolution can begin, an initial population of candidate solutions need to be created. And in order to do that, we need to come up with our representation. Well, like we just said, we're going to use a permutation representation. So a chromosome will be a list of length n. Each of the n indices correspond to each of the n queens, okay? N indices, 0 through n minus 1, and each one will correspond to an individual queen, and also kind of like which column it's in, right? Each index will be the queen's respective column, and the element within the list will be the elements, they will be some permutation, meaning each value will be unique, meaning that corresponds to the rows. And because they're unique, it's not possible to have any queens in the same row. So why can they never be in the same column? Because index 0 is where the queen in column 0 is. You can't have, there's only one index 0, only one index 1, right? And why are the rows unique? Because we have a unique permutation of the values 0 through n minus 1, meaning you can't have the same value in any of them, meaning they can't be in the same row. That's it. The only potential conflicts are the diagonals. All right, so since the values and indices are unique, no two queens be in the same row or column. An example chromosome n would be like this, right? 0, 5, 7, 6, 3, 2, 1, 4, right? Why? That's just some permutation of those numbers. I don't know if that's any good or not. It's just, it's there. So that's going to be like our encoding. A population is going to be just like a list of these chromosomes. By the way, this is not code. I'm just using like ASCII, like visualize. So what would it be? It would just be some collection of these chromosomes. That's it. How can we go about doing this? Well, here. Okay? We're going to say, okay, start with a population. It's an empty list. Population fitness. It's an empty list. We're not going to use this yet. We're going to use that later when we calculate the fitness. Right? We're going to do the same thing as the bit string, where we have two separate lists, but they're like index paired. Right? I could have done it with like a tuple or something, but I'm just going to keep two separate lists. Population for whatever in range of the population size. The chromosome will be, I'm using the sample function, right? This is like sample without replacement, I believe. So sample from what? Some like list of 0 through n minus 1. Really, that's going to return an iterable, but good enough. And pick n things, right? This is effectively shuffling, okay? What this sample does is it's take from without replacement. So think of like having a bag and being like, okay, the thing at the 0 is going to be there. And then I don't put a copy of the 0 back in. It's out.
Yeah, I use actually both methods in my algorithm. Because like I use that for one of my like genetic operators, and then for that, all I did was I just copied population like the chromosome every time, and then shuffled that because the shuffle's in place.
Perfect.
That's
Ooh, in place. You mean like it has a side effect?
Shuffle is an in place. It doesn't hurt anything, right?
Oof. That means it has a side effect. And you all know how I feel about side effects, right? To be clear, there's nothing wrong with that, right? I just want to say, like, your code has a side effect. You should use pure functions. They're better, right? But whatever. If you want to know why I didn't do it that way, it's because I don't like side effects. That's why I go out of my way to be like, give me back something. And then I append. Now, immediately after saying I don't like side effects, I'm making use of a data structure with append, which has a side effect, obviously. But data structures are different. Data structures' whole thing is adding and removing, and they are stateful. Right? So the way you could, by the way, you very well could make not stateful data structures in that where, well, what you do is every time you append, you like the old one dies and you make a new one as a copy. But like, let's not do that, okay? Yeah. Look, anyone who's obsessed with functional programming though would die on the hill saying like, no, you should do that. But don't, okay? All right. This just explains it. Any questions about this? By the way, if this makes perfect sense to you, fantastic. If you're like, well, hold on, what does that do in Python? That's not the point. Don't, forest through the trees type thing. The big picture is this is generating the population. This will give you an individual chromosome. I do that population size times, okay? Evaluation. Now this one's fun, okay? Now, let's explain this, okay? It's called attacking fitness, I'm calling it. I'm just going to read the doc string. Ugh, it's too big. All right. Count the number of attacking queens in the provided queen placements. To count each attacking pair only once, the check for attacking only happens in the forward direction from index 0 towards n. With the permutation representation, attacking can only happen in a diagonal. Thus, the check for attacking is to check only the plus minus offsets, where offset is the number of indices away the queens are from each other. For example, consider the chromosome whatever, 4, 3, 6, 1, whatever. The question marks mean I don't care what's in there. The queen at index 2, 0, 1, 2, the 4, is attacking 3 queens. It attacks the queen at index 3 as it is offset 1 and 4 minus 1 equals 3, right? So this means it's in row 4, right? It is, the 3 is 1 unit away, it's 1 index away, and its value is 1 index away. Meaning they must be in a diagonal, okay? 6 is 1, 2 away, and it has an absolute difference of 2 from the value of where it is, right? Because remember, the offset this way is like the columns, and the offset of the, index offset is the column, and the difference in the values is the rows difference. If the column difference and the rows difference is the same, exactly, right? Then it's in the diagonal. That's really the intuition. It's just, it might be kind of weird to wrap your head around it. The logic should actually be straightforward, but sometimes the code can be weird. Yes, it would have to be absolute difference because like 4 and 2, right? Because it's 2 here. All that matters is it could be here or here, right? Yeah. And we don't need to be, we're also not looking backwards, okay? Because we don't want to count attacks twice. Like if 1 is attacking 2, you don't want to count 2 attacking 1. We want to attack like attacking pairs, right? So why don't I have to worry about negative directions in the columns? Because we're only going that way, okay? But we need to check up and down for the rows to see like, okay, because it could be like this. Cool, eh? Okay, anyways, so what's the code look like? Total attackers, attacking column, attacking row, enumerate the chromosomes, right? Why enumerate? Well, because column will be the index, rows, the value in the value is like the row, right? Column row, it's pretty cool, right? Yeah, see? Yeah, I appreciate that you appreciate it. So for victim index, in range attacker column plus 1, so always start and looking at the next one. There's no sense looking backwards or at my same column. There's no other queen here. You only need to look at where my column is plus 1 to the end. That's what that is. Offset is the victim index minus the attacker column, right? Victim row will be whatever the value is at that index. Then, why am I not just doing the absolute difference? Maybe it didn't work here for some reason. Whatever, I just take the difference or the difference. I guess if I do the plus or the minus, maybe I could have done this with absolute, I don't know, whatever. I check up or down. Well, actually, you know what? I bet the reason I did it this way was for readability. I realize there's a scroll, but like it helps with the intentionality. Check if it's like up or check if it's down. That's my guess, but who knows what I was thinking years ago when I wrote this. And if it's true, if those values are the same, add 1 to the total attackers. Then, done. I think that's lovely, right? So there's our fitness, right? This just explains it. Whatever. So how do we calculate the fitness of the population? Well, just do that for each chromosome, right? Pretty straightforward. Selection, tournament. I love tournament. There. I'm pretty sure this is the exact same code, like verbatim from the other one, so nothing special there. Yes, though. What I do add here, though, is mind this direction argument, our parameter. This allows us to be like, are we minimizing or maximizing, right? By default, tournament selection says bigger fitness values are better, right? We want to maximize the integer value. Check to see for your GAs, if you're getting weird results, that your fitness is checking the right direction. You're minimizing the Euclidean distance, so you better make sure that your fitness selection is preferring smaller ones. And if you're always picking bigger ones, that could be what's causing some funny issues, so double check that. And you could tweak it by just changing this value. Direction, I changed it to -1 here because I want to minimize the number of conflicting queens. Because otherwise your selection pressure is going the wrong way, and that ain't going to help. So this is just what tournament selection, we looked at this before, right? Yeah. Tournament selection, it's just got the -1 thing there. The default value is 1. Yeah, cool. And there we go. Yeah, there we go. Yeah, cool. We just multiply it by direction. Cool. Variation operators. Here's where it gets spicy because you can't do something like 1-point crossover, right? Case in point, 0, 1, 2, 3, 4 crossed over with 4, 3, 2, 1, 0 results in 0, 1, 2, 1, 0 and 4, 3, 2, 3, 4. Which just obliterates the whole permutation thing. Like this is the worst case scenario, but it demonstrates the problem. So you can't use a crossover like this. So unfortunately, your variation operators, specifically your chromosomes, your crossovers for your permutation chromosomes are pretty hairy, okay? There's a couple of popular ones. Every year, I'm gonna warn you too, and I'm glad we're out of time right now. It's not going to be better for Friday, but I'm going to warn you on Friday, I'm going to try to explain it, and it's not going to make sense because I forgot it too. And every year I have to like re-remember, like, why the hell does this work? And like I kind of re-remember every year, so. Are you talking about the order crossover? Order crossover, yeah. So order crossover, maybe this one's not so bad. By the way, this is the first time, so something neat about Python is you can define internal functions. You can define a function inside of another function, which is an interesting feature that I never used before because I was always like, what is this? And then finally I was like, I have a use for it. Where like the order crossover is a function, and then I have another one, copy missing elements. It's a function that only matters for order crossover. Well, if later I found out otherwise, I'll just copy and paste it out. Easy peasy, right? But it only really mattered for that. And yeah, sure, I could have copy and pasted this code into here, but it would have made it a real, Code readability is important, right? So I made it its own like internal function, and this is the one and only time I've ever done it, and I'm pretty proud of that too. I thought it was quite nice. So, by the way, a little neat thing. Mutation's not so bad, swap mutation. Termination, we'll go to, like, what does this look like, right? For generation, calculate the fitness, do selection, do crossover, do mutation, repeat. That's what the other one was. The difference was, well, what was the crossover? What was the mutation? How did you calculate fitness? But abstractly, it's just fitness, exactly, right? We could have made this a function where you can pass a couple functions to it as like, this is the whatever, 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 and it would work just fine. Yeah?
I actually had a question I was thinking about when I was doing the assignment. What do you think about like the mutual exclusivity or not of various variations? So if we do a crossover, should we also do mutation? Or if we do one mutation, should we also not do the other mutation? Or should we just always just whatever?
Interesting question. Very interesting question. That is something that you can kind of play with empirically. In general, my guess is it's not really going to make much of a difference. Usually what I do is just go like, give everyone a chance for crossover, give everyone a chance for mutation. There's no discrimination between the two, right? But you very well could play those types of games. And maybe it's something fun to worth explore and say like, oh, this is kind of neat. On Friday, we will come back to order crossover. I will talk about over crossover to give you a sense of what's going on there. But if you're really stuck for your TSP, like something like order crossover, spend some time understanding that one and you'll be good to go. I'm pretty sure I give you this function though, right? Yeah, so there you go. But don't just use it, understand it. All right. Awesome. Pardon?
It's a little weird, but it works well.
It's weird and it works well. And what do we mean by work well? Well, it doesn't break the permutationness. And so it comes to up to I realize we're over time now, but I'll just finish this thought anyways. It helps with destructivity, how destructive it is, because the whole point of TSP is contiguous chunks, right? It's not that city 7 is at index 14. No, it's that city 7 is next to the thing there, which is next to there. That's what makes it good. So what's nice about this one is it allows you to have contiguous chunks that are still preserved, but the other half of it still kind of obliterates the ordering otherwise, right? So there is still some niceness there, but more on that Friday.
I liked it.
Yeah. I'm glad you did.